Hi, this is Andre again. Here's another update on the MicroPET. So today I'm going to talk about booting from SPI Flash, about some improvements on the video, some benchmarks I did with the machine, and then an outlook on version 2. Stay tuned. I've continued working on the MicroPET and the Flash ROM boot functionality. As you can see, I have succeeded to fit everything into the CPLD, and I have replaced the parallel ROM that was used to boot before, and have replaced it with a much smaller SPI Flash here on the board. And I have been able to fit in all the bootloader code into the CPLD. By removing all the ROM related code from the CPLD, I was able to fit back in the VGA output and the 8296 emulation, and even add some more custom extra SPI channels. As you can see, the machine has a new boot option, which is 8296, which separates it from the normal 8032 machines. So I'm using this one right now to show you the capabilities of the emulation. Switching from the boot menu to the actual machine takes a slight bit longer, because now it's not just copying stuff from ROM into RAM, but loading it from the SPI Flash. So let's load the test program for the 8296 and run it. So what you can see, it tests all the extension, all the memory and all the extension blocks and the logic that selects all the memory and write protection and so on. There are a couple things. It shows bad ROM UE8 at the editor ROM, which is expected because I am using a graphics keyboard with a machine that is supposed to have a business keyboard. Then there is the IEEE 488 bus and DAC bad, which is also expected because I still have the disk drive attached, and then it detects that the disk drive goes NDSC down when it also does ATN down, attention down. And then there is the bad of the 50 Hertz interrupt. And I haven't analyzed the program yet, but my assumption here is that this program counts the number of cycles that the CPU does during one display of the memory between two vertical sync signals that actually denote the 50 Hertz interrupt for that machine. And there, of course, is some discrepancy because this is a VGA output. VGA output is not totally exactly the same, because there is it's not a simple calculation, but like half of the time it's the CPU, half of the time it's the video. But basically the memory runs with 9 megahertz to get the VGA output running. So, but I'm still trying to get it run every 9 access memory access, but still well, that's probably the thing I should do next, do some kind of speed benchmark. Before we have a look at the benchmark, let's have another view on the system architecture. The last time I showed you this diagram, you may remember that on the right hand side there was the CPU, there was the I/O, and there was also the parallel ROM. As I have optimized this away using a serial SPI Flash, which is not shown here, it's connected to the CPLD. So this is what's left on the right hand side. On the left hand side there is still the video RAM. So what what I haven't shown in the previous diagram was that there also are some control lines, of which I've shown only one in this diagram. The one that's most important, that's the clock signal. That's phi 2. And this is created by the CPLD, and it's fed into the CPU as a system clock, and it's also fed into the I/O. And we have to remember that the I/O on the PET consists of a via that has timers that actually count those system clock cycles. So I will come back to that in a minute. So let's have a look how the 6502 works on memory accesses. The clock is going up and down, and it's called phase 2 because it's more or less the second half of this clock cycle. Is the one where the actual transfer of data happens. I haven't shown the data lines here, but only the address lines. The address lines change after when in phase 1, when the phase 2 is going down, then the CPU has taken over data from the bus, which is noted by this vertical line, and then the address lines change, and then the next cycle starts. Then we have another access to memory and so on, one after the other. But what happens if we have some kind of slow memory that is not capable of getting the data either written or provided to the CPU in this clock cycle? And that's what the CPU has the input that's called ready. Typically this is put on a high level, so the CPU sees that signal as an input and then says, okay, the memory is ready. But when the memory is a slow one, and what will happen is ready has to be pulled low, and then the CPU will notice, okay, there is no such thing as a memory access here, and therefore I have to not use the address here and not use the data transfer here. I do have the bus cycle here, but I have to keep my address line at the same value and just take over the data that I wanted to take over here. I have to take it over here. So that's one way of doing it, and there's another way of doing it. And that is clock stretching. If you have a slow memory, you can also just stretch the phase 2 of the clock for the second for this long for this slow memory, as long as the memory or the chip on the bus takes to do the data transfer. Yeah, those are the two ways of delaying the data transfer on the bus, but they have a significant difference concerning the via timers. This means the via timers, they count system clock cycles, like those here, or those. And as you can see here, if I have to delay the CPU, the system timer in the via will be slowed down. Now actually in the MicroPET, that's something I want to have. And the reason for that is because in the 1 megahertz mode, the system should behave like a real PET, which has a 1 megahertz clock, phi 2, and the system timer here should be running in at 1 megahertz. So what I'm doing here is I am actually stretching the clock for basically 7 cycles, and I only let the eighth cycle do the actual memory transfer. So I have a base system clock of 8 megahertz. That's for the composite video. VGA video is a little bit more complicated, but it's not important here. So I have basically very, very long stretched phi2 high, and then I have a single small phi1 phase 1 here in to start the next axis. And that makes the via count the clocks at 1 megahertz and the CPU run at 1 megahertz. But still I have the actual system clock, which is also used for example, memory access onto the video memory, running at 8 megahertz. Now this works fine as long as there is enough memory bandwidth to serve the CPU and the video all at the same time. However, when the video, the CPU is fast enough that it doesn't leave enough cycles for the video to actually display the video output, to fetch all the data for it, the video will steal cycles from the CPU. So the video circuit here will slow down the CPU like this, because this is basically what happens in 8 megahertz mode or full speed mode. But then I have an access where the video RAM, the video circuit, needs access to the video RAM to read character data or pixel data, and then the CPU is slowed down like this. In this case, I actually want to have the VIA timers run at full 8 megahertz and use the ready mechanism for that. Unfortunately, it seems there's some kind of problem still in the circuit, which I hope I will eventually iron out. But at the moment, I can only do this clock stretching. There's something wrong with this approach right now. It works well on other systems I built on the original 6502 and so on. So that should actually work, but I have to do it like this right now. So in the benchmark, and that's why I'm talking about this all the time, you will see two values, two speed values, and one is the system value, which is actually the value of the phase 2 clock here, which is used for the VIA timers. And the second one is for the CPUs, for the CPU. And the goal is to have the phase 2 clock, the system clock, scale from 1 to 4, 8 megahertz. And then on the CPU clock, where cycle stealing appears from the video, the CPU clock will be 1, 2, 4, and then maybe something around 5 to 6 megahertz, depending on video modes and so on, because of the cycle stealing for the video output. As I said, that's the long-term goal. I'm not there yet. I'm currently using clocks stretching always. So what you will see that both of those numbers are the same, because the VIA timing is basically timing the stretch clock, and that means the VIA clock is the same as the CPU clock. But hopefully I'll manage to do that in the future. But for now, it is as it is. So let's have a look at the results of the benchmark. So I have been working on a benchmark that I did for the 65816 accelerator board for the Commodore PET, and have adapted it to this machine. So let's check it out. So what you can see is the machine runs at 20,883 cycles. So this is composite video output, and it does two measurements. One is measuring the system cycles per screen vertical interrupt, which it does using the Vga versatile interface adapter timers, and the second one is running a CPU loop of a known number of clocks, and measuring also the system clock in that during that run. So the idea is to see first what is the system frequency compared to the known 50 Hz video output, and then the second is how much faster or slower the CPU is compared to that system clock. So let's have a look at the first results. So you can see of the there are 4 speed settings: 1 MHz, 2 MHz, 4 MHz, and full speed. And it scales quite nicely, except for full megahertz, which is kind of only 5.4 megahertz. What you can also see is because it's 50 hertz and there is a number more cycles, because this is now real composite video output. It seems there is a slightly more than 2 megahertz, 4 megahertz, so it's a little bit more than also than 1 megahertz, which is kind of truncated here in the display. So, but there are options too that you can do. So let's have a look at the next one. This screen shows 4 megahertz and full speed with additional options, and there is the interlace off options, which is only available on VGA output, which I haven't done yet. And there's the screen off option, which totally disables the screen during the run. And as you can see now, full screen, full speed with screen off scales exactly to 8 times the base frequency. It's just, if you look at the as long as the screen is displayed, you get less than that, because the screen has to take some cycles from the memory access. So what you can now see, I'm running the same benchmark on the VGA output with VGA timing. You can see that it's approximately 1 megahertz for 60 hertz screen refresh. So let's see how it works out. As you can see, somewhat scales, but you'll notice that because VGA takes much more memory bandwidth than composite output, it even affects the 4 megahertz setting. This is reduced to 3.4 megahertz due to cycle stealing from the VGA, and also the full speed is also reduced. Now let's look at the other settings. So now that looks kind of impressive. If you switch the screen off, you can actually see that we have up almost 10 megahertz of CPU clock, which is cool. What you also see is if you switch the interlace off, the VGA output takes even more cycles from the CPU, because it is not showing only every second pixel row, but every pixel row. So that is the penalty you have to pay if you switch off the interlace mode. So looks pretty cool, don't you think? Also, as I can convert VGA to HDMI now, let's see if I can grab HDMI into the PC and see what comes out of it. So what you can see here is a screen capture from HDMI from the MicroPET. And I have prepared something here. If you look at this memory area, you can see there is some ROM in there that I've loaded before I reset the machine. But as the reset sets the ROM area to writable, I should better make it. You can see that because there is no question mark in that monitor. I should better make it write protected. So, and now let's look what we have in drive 0. So there's Word Pro, and what I have loaded into the ROM area is the dongle ROM for Word Pro. So let's load it and see what we can do. Okay, starts up. Printer device. There is no printer device, but anyway, disk drive. Okay, so there. Oh. Okay, the space bar is a little bit, it's hanging a little bit sometimes. But there you have it. The MicroPET is ups, and that's the PETSCI keyboard from TechElect, and yeah, I have used it. I built it on a previous video, so you can see that I have put in 2 MX switches. Probably that was too much, so I have to see what I have to do here again. The MicroPET is running Word Pro. Cool. And interestingly, I haven't found out why, but Word Pro as well as VisiCalc are doing something to the machine that a normal reset is not working. I have to switch it off completely to resolve that. Nasty little bugger. I don't know why, but interesting. So switching the machine off, putting on power again, and there you have the boot screen. So cool. I can send HDMI output to a video grabber and grab it on my PC, and hopefully do some better recordings in the future. Board 2 of the MicroPET will have some significant changes, but it's still an evolution. So it will have the VGA adapter included, with an adapter connector for other adapters like composite or even HDMI. It will have a smaller power connector. I think about using micro USB or maybe something else. And then I'm planning on putting in board edge connectors, so you can use this board with your favorite extensions for the user port or cassette port, or especially the IEEE 488 cable, which is prohibitively expensive. There's one caveat with the tape ports though. There is no 9 volts for the tape drive. So, but your average adapter for communication with a PC or something like that, and getting the 5 volts from the tape port, like SD to PET, for example, does, should be working. At least that's the plan. So, I hope you like it. What do you think about version 2? Leave your comments below. Thank you for watching, and see you next time.